first I talk. Okay, so actually this session 4 today, we have a lot of speakers, including invited speaker. Mostly it's arranged based on theory, from theory. And we have several topics, starting from progenitor model, and also rotation measure and the polarization theory, of course, in application to FRB. And also, we have a bunch of talk about emission mechanism, what's going on inside the magnetosphere, especially assuming the source is magnetar. And also, finally, we have to talk about also magnetar emission itself in radio and X-ray, so which could be also related to FRB. So this is the summary, and actually, maybe Navin and also Pawan already left because of the time constraint, but we still have some invited speaker here and also online. So first, let me pick up some follow-up question. Actually, we didn't have enough question time. So are there any question to this audience, to these speakers? Okay.
Yeah, so I'm very interested about the Emmanuel's results. So,
by the way, we should solve Emmanuel should be propagation of it.
Kind of. Still.
Okay, still.
It's very difficult.
Yeah. Okay. Sorry for interruption.
yeah, if the filamentation instability happens, then the dispersion measure observed it becomes even larger, and so it's a kind of surprising results. And
is it so? I mean, my interpretation about the fragmentation along with the perpendicular to the propagation direction. And I thought that Emmanuel mentioned that, for example, induced compton scattering may be even suppressed for those directions. So I thought that DM.
Can I?
Oh, so yeah, sure, please.
Yeah, I mean, I'm here, so maybe I can say something more. So I think, can I share one moment my screen?
Sure, of course.
Or not? As you wish, okay. So, okay. I was saying yes, the dispersion measure becomes larger, but this is only the contribution of the magnetar wind to the total dispersion measure. This contribution is still small with respect to the total dispersion measure of the FRB, which is mostly for the AGM, say. But it could be important. I mean, this contribution could be important from the magnetar wind, could be important because it could be rapidly fluctuating. So this was my point.
So without filamentation instability, the dispersion measure. So for given plasma, there is a dispersion measure for homogeneous.
Yes.
And with this effect, the observed dispersion measure becomes larger, right?
Yes.
Oh, so it's very surprising.
But this effect, I mean, this effect is only relevant close to the source, because if you go far away, the problem is linear, effectively.
So my intuition is that the photon propagate in the low density region. So naive intuition. So the dispersion measure becomes smaller.
Yeah, that's my impression. You mentioned about the suppression of induced compton below, right? So I thought that waves are propagating rather in these regions, and we preferentially observe them. Then so dispersion measure even becomes a bit smaller than uniform medium.
It's the same. No. It's the same that happens. I mean, it is the same that would happen in a waveguide. If you have two conducting walls and the radiation is propagating in between, the radiation is propagating in vacuum in between, but the dispersion measure is not the same dispersion measure that you have in vacuum. The dispersion measure is determined by the separation of the two conducting walls. Because the electric field goes to zero on the walls. So this is what I'm writing here in this in the top right of the slide.
Oh, okay, thank you, Emanuele. So maybe here we also have so many people who is also interested in observing kind of effect. So you show for the first time that this kind of filamentation effect can make kind of magnetospheric plasma kind of could be very kind of so the dispersion measure from the magnetosphere plasma could be so large, right? Depending on some parameter. So how large it could be, and how large fluctuation you expect between each flare or FRB.
Okay, so we estimated this, and more or less the order of magnitude of the contribution of the magnetar wind to the total dispersion measure, which is eventually the part that is fluctuating, is of the order of tens of parsec per centimeter cube. So it's much more. So the fluctuations are much smaller than the contribution of the IGM to the dispersion measure. But the point is that this contribution from the magnetosphere, from magnetar wind, could be rapidly fluctuating. So.
Okay, thank you. So of course, depending on the magnetar and the wind parameter, this could be even larger.
Larger than 1,000?
Okay. No. I mean larger than 10, or it could be like 100 parsec per cubic centimeter, or.
This was, I mean, let's say 30 was, from our estimates, 30 was on the upper limit. 30, 40.
Okay, thank you.
Yeah, no, I don't think it could be much larger.
Okay, thank you so much.
Then it depends on many things that are not very well constrained, such as the temperature in the wind and so on. But my feeling was that a few tens was an upper limit.
So I have a follow-up question to your statement. So you mentioned that the DM variation will be around the order of 10 PC per centimeter cube. And from the plot, my understanding the time scale is roughly 1 minute. Is that correct?
Yes, here it's, I mean, this is 40 seconds that I marked here. So yes, there were cases with, I think they reported cases with fluctuations of the order of a few tens of parsecs per centimeter cube on a time scale of 10 seconds. But
right.
Yes, I mean, right. Of the order of 1 minute.
But from my understanding, usually the follow-up for the repeater, the DM variation scale is around 0.1 or like 0.01 PC per centimeter cube, which is much smaller than your estimation. And also the time scale, the DM seems like quite stable over several months. So do you have any comment on that?
I mean, so this plot that I'm showing here is observations. So the plot in the bottom right is observation of this specific FRB, and they were reporting large fluctuations of the DM on short time scales. Then these fluctuations of the DM of the dispersion measure depend on several properties of the wind. For example, the temperature or the number density, which could change significantly from burst to burst, from one source to another. So I wouldn't be surprised if in some sources we don't see significant fluctuations. I mean, it could be that the wind is a little bit hotter, and this would decrease the contribution of the wind to the dispersion measure, or it could be that the wind is a little bit less dense, and also this would decrease the contribution of the wind to the dispersion measure. So I think it's possible that in some cases, for some range of parameters, these effects are not observed, but in some cases, they are.
Okay, thank you. But it still seems like quite unusual to me. It still seems like quite a bit unusual to me. Thank you.
Okay, thank you. Any other? Thank you, Emanuele, for sharing again.
Thank you.
Okay, I share again my screen. Okay, so Okay, Tetsuya, go ahead. You have a question. Discussion.
Yes, this is just a question to another speaker today. So I have a question to Sujin's talk. So you mentioned that there is a detection of the very high frequency for magnetoplayer, say 100 gigahertz or so. So that's a very interesting to me personally. But my question doesn't make sense. But if you assuming that the SED shell, say that you detected, if you scale that, simply scale that to the luminosity of FRB, do you expect detection of high frequency counterparts of FRBs at that frequency? Say, for example, using ARMA or other radio bands. Yes. If you, for FRB case, extragalactic FRB case,
Yeah,
you just simply scale.
I think although the mechanism of the giant pulse is not known, but if we assume that still the giant pulse of the magnetar will be still related to the current normal radio pulse of the magnetar, then it also depends on the observing period from the outburst of the magnetar, because their spectrum can be changed. But if they have a still flat spectrum, then I think that the high sensitive observations using especially ALMA, maybe ALMA is available at 87 gigahertz, but we don't know because we haven't detected pulsars magnetars at that frequency range. But maybe we need more. We can try.
Yes.
Yeah.
I'm just curious. Say, if you assume the spectrum shape, then you can simply calculate the expected flux density by just scaling.
Yeah.
I'm not sure if this scaling makes sense or not, but if you just scale, then I just wonder if it's detectable using ARMA or not.
Yeah, totally. Yeah, totally it is. But our observation is not also simultaneous. So we still have a kind of 1 week gap. So
I see.
if the dual peak of the magnetar is really true, then maybe the second peak will appear around 100 gigahertz or 90 or 80 gigahertz, I expect. So, yeah.
I see.
But it should be right after the radio outburst of the magnetar, because they are usually bright in that period. So maybe we can try to use ALMA if there's any radio outburst from one galactic magnetar.
Thank you very much. That's really encouraging for using the ARMA to observe FRBs. Thank you very much.
Thank you.
So follow-up comment or suggestion is that so I discussed with Kazumi about CMB observations could be used for the FRB searches, and so if Sujin's talk is correct, so there is actually some sources at 100 gigahertz. That means the CMB detectors are actually detecting such magnetar bursts.
Although they throwing away all the
So if they know that there is a source, so they could
real fast light system can be implemented at CMB research, and that'll be especially for this audience, that'll be really exciting. So, but commercial observation with CMB.
That's a really interesting idea. I just don't know if they are really searching transient from their data, and also the time resolution of the CMB observations. I'm not sure, but in terms of frequency range, they are covering, and also all sky. So therefore, I think that's a very interesting idea. If transient is super bright, then it might be detected. Yes. Thank you very much.
I also have a question to Sujin-san for results. So you mentioned about the gigahertz peak could be due to free, and you mentioned about the scenario that free is caused by the surrounding media. But on the other hand, you said that kind of gigahertz peak is rare in radio pulsar sequence. But I thought that the radio pulsar is also surrounded by relatively sick plasma. So what's the difference?
I think I showed two slides that the direction of the line of sight can also make the peak, the position of the peak move. So yeah, maybe and also depending on the temperature and the density of the surrounding area can affect the position and the presence of the gigahertz peak. So the reason that 90% of the radio pulsar doesn't have a peak at gigahertz may be because of their surrounding area is, for example, pulsar nebula's density is not dense enough, or maybe the temperature could be a little, also could be another reason. Yeah, and the free absorption model is also still one of the possibility, I mean the kind of simulation in this model to explain that. So we still need to study more that kind of model.
Okay, thank you, Sujin. Are there any questions from the online participants? If no, I have one very general question to Yuanpei. Are you there? I see you.
Yes, I'm here.
Thank you for nice talk. I really wonder what kind of future observation, what kind of physical quantity could be really useful to, for example, constrain the small scale fluctuation of matter, which may completely hinder the true fluctuation of the rotation measure. You talk about it. So I want to know what you think.
In my opinion, I think there are some methods. One method is to calculate the strong function, because the strong function reflects the physics scenario. For example, if the medium is supersonic turbulence, we will see shadow spectrum. But for some medium not include shock, the spectrum of fluctuation would be a steep spectrum. So one method is to calculate the shock function. For different astrophysics scenario, for example, like the supernova remnant and binary system. Supernova remnants predict a long-term RM revolution and include turbulence. But for binary system, we will see the RM would be periodic, especially for the eclipse orbit. So in the future, we can test a different model via the long-term observation.
You mean long-term observation of FRB or other complementary observation? FRB.
FRB.
I see. So I just wonder how we can kind of distinguish whether the source is binary or not. So this kind of binary motion is always kind of very difficult to be kind of distinguished. So
yeah,
thank you.
Yeah, for binary signal, the smoking gun is a periodic signal, but it's measured out by turbulence. But one special scenario is like a eclipse orbit, which would have a very significant periodic signation.
Okay, thank you so much. Okay,
yes, thank you.
Thank you. Indeed, we are kind of we need to stop here. So maybe people may have more questions. So please utilize Slack channel. And thank you so much for joining today, all day. And we finish today here. And we again meet tomorrow morning, 10 a.m. Taiwan time. Okay. Right, 10 a.m. Okay. Thank you so much. 9 a.m. Sorry, excuse me. 9 a.m. tomorrow. Yes, Taiwan time.